Hello everybody, my name is Ethan. Welcome back to the channel where today we are going to be jumping back into our machine learning class within Codecedemy and going into something called regression versus classification. So in the previous episode, if we go back to the syllabus here, we'll spot that we started the machine learning fundamentals part of the class. It says it's going to take 10 hours to finish this part of the chapter. We'll see if that ends up being the case. That's obviously a long time and would have to split up into many, many videos. But we'll see how that ends up going. So in the previous episode, we finished the Welcome to Machine Learning, very simple introduction to machine learning, where we learned supervised versus unsupervised machine learning. So if you missed that episode, as well as all this stuff in here, be sure to go check it out and you'll be able to learn a little bit. So let's jump right back into it with regression versus classification. So we're going to learn about the two types of supervised learning algorithms. So again, we learned last time supervised versus unsupervised. You know what? I'm going to do this. Supervised versus unsupervised learning. So we're going to kind of jump a little bit more into supervised learning with these two classes here, regression versus classification. So machine learning is a set of many different techniques that are each suited to answering different types of questions. One way of categorizing machine learning algorithms is by using the kind of output they produce. In terms of output, two main types of machine learning models exist, those for regression and those for classification. So regression. Regression is used to predict outputs that are continuous. The outputs are quantities that can be flexibly determined based on their inputs of the model, rather than being confined to a set of possible labels. For example, predict the height of a potted plant from the amount of rainfall. Predict salary based on someone's age and availability of high-speed internet. And predict a car's miles per gallon based on size and model year, right? So we're saying that prediction is 5 centimeters. The next one goes through. It's 8 centimeters. That's the prediction. It kind of goes and keeps going, right? So my hair looks a little insane today, guys. So I apologize for that. Hopefully it's not too distracting. It definitely, I don't know, you guys. It's definitely a little crazy today, and I apologize for that. Okay, linear regression is the most popular regression algorithm and is often underrated because of its relative simplicity. In a business setting, it could be used to predict the likelihood that a customer will churn or the revenue a customer will generate. More complex models may fit the data better, but at the cost of losing simplicity. Classification. Classification is used to predict a discrete label. The output falls under a finite set of possible outcomes. Many situations only have two possible outcomes. This is called a binary classification, true, false, 1 or 0, hot dog / not hot dog, right? For example, predict whether an email is spam or not. That is a binary decision, right? Classification. An email is either spam or it's not spam, right? Predict whether it will rain or not. Obviously, very binary. Is it going to rain? Yes. Is it going to rain? No. Predict whether a user is power user or a casual user, right? That's just different classifications, so that kind of makes sense, right? Classification. There are also two other types of classification: multi-class classification and multi-label classification. Multi-class classification has the same idea behind binary classification, except instead of two possible outcomes, there are 3 or more. For example, predict whether a photo contains a pear, apple, or peach. Predict whether which letter of the alphabet is handwritten character is, and what letter of the alphabet a handwritten character is. And then predict whether a piece of fruit is small, medium, or large, right? So that's pretty simple, right? An important note about binary and multi-class classification is that in both, each outcome has one specific label. However, in multi-label classification, there are multiple possible labels for each outcome. This is useful for user segmentation, image categorization, and sentiment analysis for understanding text. To perform these classifications, we use models like naive Bayes, k-nearest neighbors, SVMs, as well as various deep learning models. An example of multi-label classification is shown below. Here, a cat and a bird are both identified in a photo showing classification model with one or more label as a result. So it highlights, no, it's not a dog. It is a cat. There is a cat in the image. I mean, there's no horse, there's no fish, but there is also a bird. Choosing a model is a critical step in the machine learning process. It is important that the model fits the question at hand. When you choose the right model, you are already one step closer to getting a meaningful and interesting results. Very simple. All right, here we go. Intro to linear regression. Now, if you're not familiar with linear regression, this might be a little bit tough for you, but hopefully we can do this. The purpose of machine learning is often to create a model that explains some real-world data so that we can predict what may happen next with different inputs. The simplest model that we can fit to data is a line. When we are trying to find a line that fits the set of data, we are performing linear regression. We often want to find lines to fit data so that we can predict unknowns. For example, the market price of a house versus the square footage of the house. Can we predict how much a house will sell for given its size? The tax rate of a country versus its GDP. Can we predict taxation based on a country's GDP? The amount of chips left in the bag versus number of chips taken. Can we predict how much longer this bag of chips will last, and given how many people at the party have been eating? Imagine we had a set of weights plotted against heights of a large set of professional baseball players, right? To create a linear model, we would draw this line. Now, if we wanted to estimate the weight of a player with height of 73 inches, we could estimate that that is around 143 pounds. A line is a rough approximation, but it allows us the ability to explain and predict variables that have linear relationship with each other. In the rest of this lesson, we'll learn how to perform linear regression. So we're going to run the code in script.py. This shows Sandra's lemonade stand revenue over its first 12 months of being open. Boom, boom, boom. From eyeballing the graph, what do you think the revenue in month 13 would be? Enter your approximate answer in a variable called month 13. So on month 13, we assume it's going to go up another half step, right? So on another half step, we'll assume it's over 180, right? So we would enter, again, we're just going to, we're going to enter a variable called month 13, and I'm going to set it equal to 180, maybe 187, something like that. Perfect. Points and lines. In the last exercise, you were probably able to make a rough estimate about the next data point for Sandra's lemonade stand without thinking about it too hard. For a program to make the same level of guess, we have to determine what a line would look like through those data points. A line is determined by its slope and intercept. In other words, for each point y on a line, we can say y equals mx plus b, where m is the slope, b is the intercept, and y is the given point on the y-axis and corresponds to a given x on the x-axis. Hopefully, you know y equals mx plus b. The slope is a measure of how steep the line is, while the intercept is a measure of where the line hits the y-axis. When we perform linear regression, the goal is to get a best m and b for our data. We'll determine what best means in the next exercises. We have a slope m and an intercept b that seem to describe the revenue data you've been given. Create a new list y that has every element in months multiplied by m and added to b. A list comprehension is the easiest way to do this. Okay. So it wants me to create a new list. New list is equal to, I guess that's not how really Python does it. List comprehension, been a minute. So let me think. We could create a new list, and then what I would do is I would do a for loop. So I would do for month in months, month new value is equal to month times m plus b, new list dot append, and then we put the value of new value. That's how I would do it, but we'll see if that's what they wanted us to define y. Create a new list y. 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 Perfect. I'm sure there was an easier way to do that. Yeah, so it wants me to do list comprehension. Slope times x value plus for x value in x values. You see. Plot the y value against months as a line on the top of the scatter plot that was plotted in. Plot the y values against month as a line on the top of the scatter plot that was plotted in plot. Dots. It's like add linear or whatever. To plot a line, you can use the syntax. Make both plot calls before you call show. I see. The month is the I think I did it correct. Change M and B so the values you think match the data best. So if I look at it right, we got 80 to 20, so that's a rise over run, 40 slope, right? Slope of 8 is a little too low. Let's try a slope of 12. That seems a little bit better, right? That looks good. Loss. When we think about how we can assign a slope and intercept to fit a set of points, we have to define what is the best fit. For each data point, we calculate a loss, a number that measures how bad the model is. In this case, the line prediction was. You may have seen this be referred to as an error. You can think about a loss as the squared distance from the point to the line. We do the squared distance instead of just the distance so that the points above and below the line both contribute to the total loss in the same way. For example, point A's squared distance is 9, right? And for point B, the squared distance is 1. So the total loss in this model is 10. If we found a line that had a less than 10 loss, the line would be better for this model. We have 3 points here. So we have the first one is 1, 5, 2, 1, and 3, 3. We're trying to find a line that produces the lowest loss. We've provided a list of the x values and y values for these points. Find the y values that the line with weights m1 and b1 would predict for the lines. So, and store this in y predicted 1. Okay. So y is equal to and it probably wants me to do the list comprehension again. So we'll do it actually how do they do it now? M1 times, oh boy, x value, y value plus b1 for y value in y. Okay, what did it want me to do? Well, that's pretty interesting. Let's take a peek under the hood and see what I've messed up on. Why does it want me to use X? Predict the X values given. So I just have to change find the values of y with weights that would predict the values given. So then we still want to do that. Predicted 2 is equal to the lowest comprehension m2 times, can I find it, x value plus b2 for x value in x. Create a variable called total loss 1, set it equal to 0. Then find the sum of the squared distance between the actual y values of the points and the predicted y values by looping through the list, calculating the difference between squaring the difference and adding it to total loss. Okay. So for So it wants me to find the sum of the squared by predicted values by looping through the list. Calculate the difference by subtracting y and y predicted. How would you start your for loop there? You'd start it by saying for y value in if I say print y value, what happens? It's not going to be right. For I know it's IDX in my range. I'm messing up here. For y value in y, print y. How about that? 5, 1, 3. Okay. So it wants me to probably do a nested loop for I in right. Like, dude, that's exactly what I did. Range length, I think, is what I wanted instead. Whatever. For IDX in range length y. That's so annoying, though, because I knew I wanted to do indexing of the list. It's just whatever. Y indexed at IDX minus y predict. We done to do the first one. Predicted 1 at index IDX, and we'll set that equal to a variable called we'll just say this is the difference is equal to y, right? And then we'll say we'll say diff squared. Oh my god, what's my typing today? It's equal to difference times 2, and then we'll say total loss 1 is plus equals diff square. If I can spell squared today, I'll do it. That's so annoying. I just misput. I did length range, but it was range length. I don't know. So it's fine. Gonna do the same thing here. Do total loss 2, set it equal to 0 for IDX in range length y. We'll do difference is equal to y IDX minus y predicted to at the IDX, and we'll do diff squared is equal to difference we'll print them both now. Create a variable and assign it to 1. If we'll create a variable called better fit equal to none. If total loss 1 greater than total loss 2, better fit is equal to 1. We want less. So if it's, let's say if it's less than, set it equal to 1. Else better fit equals 2. Perfect. Perfect, perfect, perfect. We're on 4 of 13, already 23 minutes in, guys, we're cooked. Okay, minimizing loss. The goal of linear regression model is to find the slope and intercept pair that minimizes loss on average across all of the data. The interactive visualizer in the browser lets you try the line of best fit for a random set of data points. The slider on the left controls the slope, and the slider on the right controls the intercept. You can see the total loss on the right-hand side of the visualization. To get the line of best fit, we want this loss to be as small as possible. To check if you got the less fine, check the best plot fit box. Randomize a new set of points and try and fit a new line by entering the number of points you want to try. 8. Try 8. 8 points. Randomized points. So it's just saying play with the interactive to try and get the line of best fit, right? So if I lower the thing, as you can see, it skyrockets there. Oh, it kind of peaks down low, going back up here. And it looks like when I get down to that 233, that's the lowest. But now if I start my thing off, That looks like the best plot fit line. Let's check. Looks like I might have it, you guys. Very nice. Did you get the first slope where it produces the lowest and then move the intercept where it produces lowest loss? Do you create a rough idea in your mind where the line should be? Right? Yeah, that makes the most sense to me. We're minimizing. We're trying to minimize the total squared error. Gradient descent for intercept. As we try to minimize loss, we'll take each parameter we are changing and move it as long as we are decreasing loss. It's like we're moving on down a hill, and stop once we reach the bottom. The process by which we do this is called gradient descent. We move in the direction that decreases our loss the most. Gradient refers to the slope of the curve at any point. For example, let's say we are trying to find the intercept for a line. We currently have a guess of 10 for the intercept at a point 10 in the curve. The slope is downward, therefore, if we increase the intercept, we should be lowering the loss, so we follow the gradient downwards. To derive these gradients using calculus, it's not crucial to understand how we arrive at the gradient equation, but to find the gradient of loss as intercept changes, the formula comes to this. I'm not going to say that out loud. But n is the number of points we have in our data set, m is the current gradient guess, and b is the current intercept guess. Basically, we find the sum of y value minus y times x value plus b for all values of y and x we have. Then we multiply the sum by the factor of -2 over n. N is the number of points we have. Define a function called getGradient at b. We'll do that. Gradient at b. We're defining a function actually. So define gradient at b. B. Return b. In the get gradient at b, it takes in a set of values x. Reading step 1. I'm glad I put DMX Monkey up. I didn't know if I remembered today, actually. I just noticed in the camera, though, that he is in there. Because I got 2 monitors. I got one. Honestly, you know what, guys? Let's take a 2-second break if you're in the video here. Oh my god, my room is so dirty. Never mind. We're not going to do that. Hopefully nobody saw that. Okay. In the gradient at b function, we want to go through all the x values of y and compute y minus mx plus b for each of them. Create a variable called diff that has the sum of all these values. So, for right now, we're going to get rid of this return b statement. And instead, we are going to, we want to go through all of the x values and all of the y values and compute y equals mx plus b for each of them. Create a variable. So, we're going to have to create a variable called diff, and we're going to set it equal to 0, right? And then we're going to use a for loop, and we're going to say for idx in range length y. And what we will do is we'll set this variable to equal loop diff. That is the difference that we find in just that one loop. And we'll say that that is equal to y at the index, right? And for right now, I will surround this in some parentheses so that we are staying with what we want here. And we'll add another set, and we'll say m times x at the idx, or index, plus b. And then once we have that loop diff, we'll say diff plus equals loop diff, right? Function returns none when it should have returned -2. With the inputs, okay. X. Okay, let me see what it wants me to do here. Return none because I didn't have a return statement. I didn't do any of the coding wrong. I just actually got rid of my return statement. So it wants me to return diff. Simple as that, guys. Read your instructions. Return diff. It literally says it at the last second there. Still in the gradient fb function, define a variable called b gradient and set it equal to -2n multiplied by diff. N is the number of points, i.e. the length of x list or y list. Instead of returning diff, return b gradient. So still in this function, we are going to define a new variable called b gradient and set it equal to, I'm going to set it equal to -2 divided by n multiplied by difference. So multiplied by diff, but so I'm going to actually then move this b gradient variable after this for loop so that I know for fact the for loop has ran. So before that, we're going to also define a new variable called n, and n, this should be inside the loop, yep, n should be equal to, do I have cap lock on? Yes, I do. N should be equal to the length of the x value list or the y value list. So we'll just do length of x, right? And again, remembering our return statement, we have to return b gradient. Perfect. So now this function works. So we get our gradient, right? Depending on what values we put in for x, y, m, and b, it's going to tell us if it's a downward slope, upward slope, what we should be doing. Cool. Gradient descent for slope. We have the function to find the gradient b, and they, of course, changed mine a little bit, so that's fine. We have a function to find the gradient of b at every point. To find the m gradient, or the way the loss changes at a slope of our line changes, we can use this formula. So again, that -2 over n. I'm not going to read the rest out, but n is the number of points you have in your data set, m is the current gradient guess, and b is the current intercept guess. To find the m gradient, we have the sum of the x value times that original value of that b gradient there for all the y values and x values we have, and then we multiply it by a factor of -2 over n. Once we have a way to calculate both the m gradient and the b gradient, we'll be able to follow both of these gradients downward towards the point of lowest loss for both the m value and b value. Then we'll have the best m and the best b for our data set. So we're going to define a new function down below here called define, or not called define, but define gradient at, and this time it's going to be m, and it should take a set of values of for x, for y, m, and b. And in this, right now, we're just going to have it return m. Cool. I'm going to get rid of that return statement. We're going to try and remember not to mess it up this time, but in this function, we want to go through all the x values and y values and compute x times for each of them, create a variable called diff that has all the sum of these values. So again, I'm going to create a diff variable that has the value of 0, and then I'm going to create a for loop that loops through the index of the for idx in range length y. You could put y or x here, really doesn't matter, but for that we are going to have our loop difference. I'm going to set that loop difference equal to this kind of value here, right? So I'll do that by doing x at the idx, or the index times the let's open up a parenthesis there, so then y at the idx minus, and then we'll do one last parenthesis here, and we'll do m value times the x at the idx plus the b value. And with that loop difference, we can now do difference plus equals loop difference, and that should give us what we want, right? But of course, I forgot again to return loop diff. It's going to return none if we don't have a return statement. It says it should have our function returned -2 when it should have returned -3. So let's just make sure that everything is correct here. Y minus mx plus b. We did plus that b value. That's interesting. Sum of all those values and return it from the function. Go through all the x values, goes through all the y values. So diff starts at 0, plus equals loop diff. Loop diff is equal to x at that value. Let's take a peek at the solution. I know it's going to still use that same thing there, but I should be chilling. This shouldn't matter, but maybe. I mean, the difference plus equals x value times y value minus. This has some parentheses around it. Then this one. Then that one. What is going on, you guys? Okay. Let's just do it how they wanted us to do it, right? Oh, I'm returning loop diff. What am I doing, you guys? I'm returning loop diff. Okay, so define a variable called mgradient and set it equal to -2 over n multiplied by n difference. So again, I'm going to go below here and do m gradient is equal to -2 divided by n times that diff variable, and then of course up here we'll set n equal to length of x, and instead of returning diff here we want to return m. Oh, why is it asking for suggestions? We want to return m gradient. Perfect. Put it together. Now that we know how to calculate the gradient, we want to take a step in that direction. However, it's important to think about whether that step is too big or too small. We want to overshoot the minimum error. We can scale the size of the step by multiplying the gradient by a learning rate. To find a new b value, we would say new b is equal to current b minus learning rate times the b gradient, where current b is our guess for what the b value is. B gradient is the gradient of the loss curve at our current guess, and learning rate is proportional to the size of the step we want to take. In a few exercises, we'll talk about the implications of a large or small learning rate, but for now, let's use a fairly small value. We're going to define a new function called step gradient. It wants us to define it here. That takes x, y, current b, and current m as arguments. This function will find the gradients at b current, m current, and then return new b and m values that have been moved in that direction. For now, let's just return the pair. Okay, so for right now, we're going to define a new function called step gradient that has the values of x, y, b, b current. I have OCD, I guess. I don't know what I have. B current and M current. And for right now, we just want it to return the pair of B current and M current. Perfect, which is just 0 and 0. Oh, well, actually, that's probably something that's up here. Yeah, that's just what that is, right? Okay, so now step 2 says that inside of step gradient, find the gradient at B current and the gradient M current using the functions defined before. get gradient at b and get gradient at m. Store these gradients in variables called b gradient and m gradient and return these from the function instead of b current and m current. So we will do that by, I'll first do a new variable called b gradient, set that equal to the function get gradient at b with the value of b current. Then I'll also do m gradient is equal to get gradient at b, or at m, sorry, with m current as the variable. Then what it wants me to do is return, instead of b current and m current, it wants us to return b gradient and m gradient. Get gradient at b. We have to enter in the other arguments here. So b current, that's actually, yeah, that's pretty wrong. Inside step gradient, find the gradient of b gradient and gradient using the functions, right? But we don't have any other stuff to find because months and revenue are right there. Let's see what it wants me to do. I see. We're defining a function. What am I talking about? My apologies. Much better. That was a big mistake. Okay. Let's try to move on to parameter values in the direction of the gradient at rate 0.01. Create a variable called b and m. B should be current, b minus m should return the pair, the function. So let's create two new variables called b is equal to b current minus 0.01 times b gradient, and then m is the same thing, just m instead of b, right? And it wants us to, should have returned cool. We have provided Sandra's lemonade data once more. We have a guess for what we think b and m might be. Call your function to perform one step of gradient descent. Store the results in b and m. Great. We have a way to step a new b and m values. Next, we will call a function a bunch in order to move those values towards lower and lower lost. Okay, so it wants me to call the function. Call your function to perform one step of gradient descent. I see. Because we're returning both b and m is equal to cool. Forgot about that. We were returning the two values here. Convergence. How do we know when we should stop changing parameters m and b, and how will we know when our program has learned enough? To answer this, we have to define convergence. Convergence was the stop loss changing or changes very slowly when parameters are changed. Hopefully the algorithm will converge at the best values for the parameter m and b. Run the file, look at the graph. This so let's just click run. This graph shows how much the parameter b has changed with each iteration of gradient descent runner. How many iterations did it take for this program to converge? Enter your answer in a variable called num iterations. So it looks like it took about 800-ish, maybe 900 iterations. If we go up right from 800, yeah, it looks like it's really starting to flat around 800. So I'll say num iterations is equal to 800. At what b value did this program converge? So it looks like the b value of about 45 is what it was converging to, just from the eye test here. Love that. Cool. Learning rate. We want our program to be able to iteratively, what is this? Let's learn today, guys. Let's learn some new words.
Iterative.
Iteratively learn over iterations, right? We want our program to be able to iteratively learn what is the best m and b values are. So for each m and b pair that we guess, we want to move them in the direction of the gradients we've calculated, but how far do we move in that direction? We have to choose the learning rate, which will determine how far down the loss curve we go. A small learning rate will take a long time to converge. You might think you might run out of time or cycles before getting an answer. A large learning rate might skip over the best value and might never converge. Oh no. We've imported two new lists representing how b values change with different learning rates. B that 1,400 iterations of gradient descent on b with learning rate of blah. 100 iterations with learning rate of 0.01. Change the plot to plot BS. Iterations. Oh, I see. So it wants me to do BS underscore 1. I don't know how that's. It didn't actually check it. Change the plot to plot BS 0. 0.1 instead of, unfortunately our computers blew up after 100 iterations of this, so you also have to change the number of iterations to 100 instead of 1400, right? Does the gradient algorithm still converge to the same b value? In this case it looks like a straight line, so the b value just keeps growing. There was no actual curve when I did this, at least is what I'm seeing here. This time it's completely opposite. It looks very strange. Blew up to, yeah, that value. Gotcha. Put it together too. At each step, we have learned how to calculate the gradient and move in that direction with a step size proportional to our learning rate. Next, we want to make these steps until we reach convergence. We have all the functions we have defined throughout the lesson. Let's create a function called gradient descent that takes in x, y, learning rate, and num iterations. For now, return -1, -1. Okay. So we want to, your gradient descent function goes here. So again, we'll define a new function called gradient descent, and it'll take in the values of x, y, learning rate, and num iterations. Oh, come on. And for right now, we just want to return the value of this list of -1, -1. And that should be fine. In the function gradient descent, create variables b is equal to 0, m is equal to 0. We want to return b and m. Update your step gradient function and to take in the parameter learning rate as the last parameter and replace the 0.01 in the calculations of b gradient and m gradient with learning rate. So if we go back up here, we want to add a new one called learning rate, and then instead of this right here, we'll add in that value of learning rate, and down on learning rate. Let's go back and finish the gradient descent function. In the gradient descent function, create a loop that runs num iteration times. Create a loop that runs at each step. It should call the step gradient function, learning rate, update the values of b and m with the values step gradient returns. So it wants us to add a new loop. For how'd they do this? Do they do a for loop? For I in range numerations. Yeah, that makes sense. Okay. For I in, and I'm going to just stick to my index in range num iterations, and I didn't want to look at the other thing just so I can do it myself. I didn't want to actually look at the body of the code. I just wanted to see if they did a for loop. At each step, it should update the values b comma m is equal to step gradient b or x y b. Oh, I guess it's for step gradient. It starts with the b. So b value, m value, m value. Then we have our x value, our y values, and then our learning rate. Outside of this function, uncomment the lines that call gradient descent. Comment the lines that will plot it to the browser. There we go. Boom. Use your functions on real data. We have constructed a way to find the best b and m values using gradient descent. Let's try this on the set of baseball player heights and weights that we saw at the beginning of the lesson. Run the script. This is a scatter plot of weight versus height. We've imported gradient descent function, call it with the parameters. So we'll do that by imported. We'll say b and m is equal to gradient descent with the values of x, comma, y, comma, learning rate of 0.0001 and the num iterations of 1000. Is this going to work? is the question. The plot loaded. It's taking quite a long time though. It worked. Okay. Create a list called Y prediction. Set it to be every element of X and multiplied by Y. The easiest way to do this would be a list comprehension. So it tells me that we should do a Y predictions is equal to a list, and then we want to do B or M times X plus B for X value in X. I wonder if it'll take a long time this time. It will, apparently. Series objects are mutable. This is a series. Yeah, it is a series. I'm stupid. And now we have to pay for it because I have to wait. Very frustrating. It's now going to ask me to plot X versus predictions on the same scatter plot. Does the line look right? Okay, so now we want to do plt.plot. For my X values, we'll just do X. For my Y values, we'll do Y. Predictions. Let's see what happens. Hopefully you should see a line that kind of, if it makes sense here, kind of should go up, it looks like, in my opinion. Maybe, yeah, that looks good as well. Let's see if I did it correctly, though. Let's go into the solution and make sure I did it correct. Yes, I did. Okay, never mind. We're good. Scikit-learn. Congratulations, you've now built a linear regression algorithm from scratch. Luckily, we don't have to do this every time we want to use linear regression. We can use Python's scikit library or scikit-learn. Let's maybe scikit. It looks like science, so scikit-learn. Or sklearn, you know, we don't say sklearn apparently. We learned that last time, I think. So we don't say sklearn, but we'll say sklearn or scikit library. It's specifically used for machine learning. Inside the linear module, there is a linear regression function we can use. So from sklearn.linear model, import linear regression. You can first create a linear regression model and then fit it to your X and Y data. So we say line fitter is equal to linear regression, and then line fitter.fit. The .fit method gives the model two variables that are useful to us, the linefitter.coefficient, which contains the slope, and the linefitter.intercept, which contains the intercept. We can also use the predict function to pass in X values that receive the Y values that this line would predict, right? Note the number of iterations and learning rate you learned about in your own implementation have been default values within scikit-learn, so you don't need to worry about setting them specifically. We've imported a data set of soup sales versus temperature. Run the code to see the scatter plot. Can you envision what the line of best fit would be? So it looks like it would be more of a downward sloping curve, line. So let's create a sklearn thing and call it line fitter. So we'll say line fitter is equal to, and it wants me to do that linear regression. And then we're going to do that line fitter dot fit, and we'll use temperature and sales. So next we are going to get a sales predict. The line fitter would generate from the this is probably list comprehension if I had to guess. You can use the predict model of the line fitter, pass in the temperature as it and call it. Oh, actually we might not have to. It might just do it for us. So if we do this line fitter dot predict using the generate from the temperature list, we'll put in temperature. We'll get that line, and now we want to before we plot this, we'll do plt dot plot, and then we'll put the same temperature, and in this time in this line we'll do just the predict, and this makes it a lot easier, obviously, as you can see. How would you actually do this? I think what we would have to do is just move this all down. And yeah, we get that nice downward sloping curve. All right, review. We have seen how to implement a linear regression algorithm in Python and how to use the linear regression model from scikit-learn. We learned we can measure how well a line fits by measuring loss. The goal of linear regression is to minimize loss. To find the line of best fit, we try to find the b value, intercept, and m value slope that minimize loss. Convergent refers to when the parameters stop changing with each iteration. Learning rate refers to how much the parameters are changed on each iteration, and we can use scikit-learn's linear regression model to perform linear regression on a set of points. These are important tools to have in your toolkit as you continue your exploration of data science. Okay, so that's going to do it for today's video. In the next video, we can click up next and see what we're going to be getting into. Oh, I guess we can actually do the quiz here. It's only an 8-question quiz. We might end up having a project too, if I had to guess. Yep, we will have a project. Shoot. Let me think. I think we can just get that done, and I thought I was going to end the video, but obviously we're going to do one. If we're going to do the linear regression, we're going to do all in one video here. So when does linear regression algorithm stop? When the parameters stop changing or change very slowly, right? So let's say we have 3 lines that produce the following average loss on our data. Which line is the line of best fit? So it's going to be the smallest loss, so I'm going to say line B. If this model worked correctly, what should y new represent in the code below? So we have the linear regression, we fit that, and then we're going to predict it. So the predicted it's the predicted y values from a new set of x values, right? The y values that x would produce on the line of best fit. Okay, that's fine. Okay, which of these lines seems to fit the best data? I'd say not line B, not line, but somewhere in the middle, so that line A probably would fit. What is the purpose of performing gradient descent? To move parameters in the direction that minimizes loss. Right, cool. If the algorithm is taking too long to converge, what should you move the learning rate up or down? The learning rate should go up if it's taking too long. The goal of linear regression algorithm is to find the blank and blank that minimize, so the slope and the intercept that minimize. And last question here, what is the sum of the squared error between the points described by x values and y values described by m and b? So what is the sum of the squared error between the points described by x? So points on the line, so this equals 0, it's squared, so it's 4 minus 3. Why are they going to make me do math right here? It's not 0 because we're going to have something here. So value of points described. What is the sum of the squared? So you take the points on the line and subtract the predicted value. So 1 minus 1 is 0. Negative 3 minus 4 is positive 1 squared is 1. Negative 6 minus 7 is 1 squared is 1. Negative 8 minus 6 is negative 2 squared is 4. So I'm going to say 6. Yep. There we go. Perfect. Let's continue learning. Missed one, and that was pretty stupid, but now we have our project. Now that you have learned how linear regression works, let's try an example of real-world data. As you may have already heard, the honeybees are a precarious state right now. You may have seen the articles about the decline of the honeybee population for various reasons. If you want to investigate this decline and how the trends of the past predict the future for honeybees. Note, all the tasks can be completed using Pandas or NumPy. Pick whichever one you prefer. If you get stuck during the project, you could also do the walkthrough video. So check out the data frame. It is called DF and has the following columns. Use head to get a sense of how this data is structured. So if we do df.head, and I'm going to just do the first 5 rows of the head or of the data frame, we can do that by actually printing it out and not being a noob when it comes to data science. Come on now. Cool. We get the first 5 rows, kind of see how that looks. Okay, that's pretty cool. Now it wants me to, we care about the total production of honey per year. Use the group by method provided by Pandas to get the mean of the total production per year. Store this in a variable called production per year. We care about the total production of honey method in Pandas to get the mean of the total production per year. So if we did a prod per year is equal to data frame dot group by, and then we'll group by the it wants us to group by the total prod column, which is this one here, and then we'll do dot mean. Oh my, and I just full screened it somehow. That was silly. It's because I'm trying to delete that. I hate doing that. Attribute group by. Let's see what that looks like. Data frame dot group by year dot total prod group per year. We want to actually group by year, and then do dot total prod dot mean dot what is the reset index, dot reset index. I'm not familiar with that dot, but I will put it in just because. So it wanted us to group by year. Data frame has no. Data frame is equal to, so it's getting mad at me for putting df. Oh, because I'm, my God. It is just dot group by. So we've now grouped by, create a variable called x, that is the column of the years in the prod per year data frame. That is the column of years in the data. Okay. Create a variable called x, that is the column of years in this prod per year data frame. After creating x, you'll need to reshape to get the right format using this command. We want to use it as the column of year. That is the column of years in the. So we'll just do prod per year data frame with year as the title, and then we'll do the command that it wants me to do, which is x is equal to x dot values dot reshape dot -1 -1. See, I literally just did that. Okay, that's what I did. Let's save it again, see what happens. Traceback file, script.py, line 12. X equals x dot values dot reshape. See, it wants me to do this reshape. I don't know what I'm doing with that. I don't know exactly what that's even doing. After creating x, we need to reshape it to get it in the right format. Oh, it doesn't want the negative. It just wants 1. I thought it wanted -1, -1. Some reason that's different. Create a variable called y that is the total prod column in the prod per year data set. So y is equal to prod per year. And then we want it as the total prod column. We can X that off. Now, using plot.scatter, plot x versus y. Yeah. plt dot scatter x versus y. And then we'll display it by doing plt.show, pld.show. Can you see a vaguely linear relationship between these variables? Yes, there's a vague downward sloping linear variable there. Relationship, I mean. Cool. Sounds like we're doing pretty good so far. Okay, let's create a linear regression model from scikit-learn and called it regression. So we should have already imported linear model. From import linear model. So I guess I can just do regr is equal to linear regression. Just that, right? Yeah. Oh boy. I see. I see. Because in the earlier one, we actually imported linear regression, so we didn't need to do this before. And linear regression classes linear to assign as a variable. Yeah. Okay. Fit the model using the fit function, and you can feed x into your linear regression by passing it as a parameter of .fit. After you fit the model, print out the slope of the line stored in a variable called regression.coefficient and the intercept. Yeah, okay. So we can first do the fit function by saying dot fit x and y. If we do that, does it want us? You can feed x into it by passing it as a parameter and dot fit. So we just ran the function. It doesn't want us to set it equal to a variable. And then after you have fit the model, print out the slope. So we can do that by doing print dot coefficient underscore and then dot intercept underscore. And it looks like when it printed it out, it printed it as a variable in a list. So we can, if we need to, as you may have spotted, put it as 0 and get it out of that list and just as a value. We printed both of them out. Now let's create a list called yPredict. That is the predictions of your regression model would make on the x data. So we're going to create a variable called yPredict, set it equal to a, what was the function? I like how they like go through step by step on how to make it yourself and then do one slide of the model, but then in the project they make you do the scikit-learn or whatever. I'm gonna say sklern. Fuck you guys. I'm saying sklern. I'm not actually, because that's just sounds weird. But what is the function? The predict method. Yep. So regression dot predict using the x values. Plot prediction. We're gonna do Control C, Control V. Put this plot to the bottom. It's trying to find something in my text. I don't want it to. Then we're going to do a plt.plot. And we'll put x comma y predict. And now we see that line, which it's really nice looking. And I assume this might be the color when we do, like when they do that O, that makes it orange. Oh my, I bricked the code here, so let's just get rid of that. Wow, I really made the code really mess up. Okay, predict the honey decline. So it looks like the production of honey has been in a decline according to this linear model. Let's predict what the year 2050 might look like from terms of honey production. Our known data set stops at the year 2013, so let's create a NumPy array called xFuture. That is the range from 2013 to 2015. The code below makes a NumPy array with the numbers 1 through 10. Is the range from 2013 to 2050. So it wants me to say xFuture is equal to np.array range starting at 2013 and all the way up to 2051. We'll just include that other one, right? And then after creating the array, we need to reshape it for scikit-learn. So we say xFuture is equal to xFuture dot reshape -1 1. You can think of reshape as rotating this array rather than one big row of numbers. xFuture is now a big column of numbers. There's now one row in each number, or one number in each row. Reshape is a little tricky. It might help to print out xFuture before and after reshaping. Honestly, let's do that just to see how it looks. So just so we can actually see what it looks like. Okay, so before it's one big column or one big list, and after it's a list of lists. So that might actually help us kind of understand what that reshape is doing, right? Okay, let's save it so we can actually see what's going on inside our console. Alright, let's create a list called future predict. That is the y values that your regression model will predict of the future values of x. So we'll do this by doing future predict, set it equal to regress.predict with the values of x future. Plot future predict. So now again I'm going to just move this down. Plot future predict. Oh, it wants me to do it on a separate plot. So we'll do that by doing plt.scatter. X future y. And then we'll do plt.plot x future and y, or future predict. We'll do plt.show. Okay, x and y must be the same size. How helpful. If I instead were to comment out the previous plot, what happens? Line 32 it's not liking, which is this one because they're not the same size. So plot future predict versus x predict on a different plot. if we just get rid of this and do this. I see. I think that looks good. I mean, we don't actually have data values in here. We just actually see that the variables are going way low. That makes sense. All right, that actually does now finish up the stuff. So in the next episode, we'll learn about multiple linear regression. We just did linear regression or simple linear regression in this episode, but we'll do that in the next one. Thank you guys so much for watching. Hope you did enjoy. If you did, please be sure to leave a like, subscribe, comment down below if you have any questions, comments, or concerns. Thank you very much. Have a good rest of your day. Peace out.